Every year, this Norman window problem gives everybody a hard time. So if you want a couple of hints to kind of help you get started on it, check this video out. Now, a Norman window is one in which the frame it consists of a rectangle and a semicircle placed on top of it. In this example, we want to find the maximum area we can get if the frame can only use 16 feet of material. Now, if we want to maximize the area, we're going to need an area function. So to come up with that, we think this window is made up of a rectangle and a semicircle. So the area of that semicircle is going to be 1/2 of the area of a circle, pi r squared, where this is our radius. And then we also have to add in the area of the rectangle, which is just base times height. Now, having all of these variables in our area function is not going to be very helpful for us. What would be more helpful is we can come up with an area function just in terms of x. Well, taking it just piece by piece, first of all, this 1/2 pi r squared, we can go pi over 2, and take a look at the radius in terms of x. Well, since the radius is really just half of this length, that means the radius is going to be x over 2. And turning our attention to the rectangle, x times y, we're going to need to replace y with some sort of expression in terms of x. To do that, we turn our attention to the amount of material that's used. That's 16 feet. And we think about, where does that 16 feet come from? Well, in the frame we have both of these x's and both of these y's and this entire semicircle. So the circumference of the semicircle is going to be 1/2 of 2 pi r. Now there's a certain amount of rearranging and substituting and simplifying that we can do to help solve this for y. First of all, I recognize that every term is divisible by 2, so I'm going to divide all of these by 2, and we'll have 8 is equal to the x plus y, and then plus 1/2 of pi times r. And we already know that our radius is half of what x is. Then when we solve for y, we're going to start with that 8, subtract off that first x, and then subtract off our 1/2 pi times x over 2. Well, half of pi is pi over 2 times that other half means we've got pi over 4 times our x. That's enough to substitute back into our expression right here. 8 minus x minus pi over 4x. Currently, this area function, it's all in terms of x, which is great, but it's kind of messy. And we know that eventually we're going to have to take the derivative of this in order to find those critical points. So it might be a good idea to simplify this equation before we get into finding that derivative. So to do that, in this first term, I'm going to take out the x squared, and I'll be left with pi over 2 times 1/2 squared, which is 1/4, and then we'll have our x squared outside. In the second term, I'm going to distribute that x, so we'll have 8x minus x squared minus pi over 4x squared. Cleaning things up a little bit more, we've got pi over 8 x squared, our 8x minus x squared minus pi over 4x squared. Now with all those x squared terms, I'm just going to collect those coefficients, and we'll have pi over 8 minus 1 minus pi over 4 x squared. And we'll still have that plus 8x off to the side. Now inside that parentheses, we can clean it up a little bit more. 1/8 minus 1/4, that leaves us with negative 1/8, so we got negative pi over 8 minus 1. That's going to be our coefficient for the x squared term, and 8x for our x term. So, to get us started, that's what we're going to have to take the derivative of in order to find our critical points. You could take it from there.